Let us begin with a brief introduction about what naive Bayes is and why it is called that, and then we will straight away dive into the mathematical aspects related to it. The naive Bayes algorithm is a machine learning algorithm for classification problems. It is primarily used for text classification, which involves high-dimensional training data sets. A few examples are spam filtration, sentimental analysis, and classifying news articles. It is not only known for its simplicity, but also for its effectiveness. With the naive Bayes algorithm, you can build models fast and make quick predictions. This algorithm learns the probability of an object with certain features belonging to a particular group and class. In short, it's a probabilistic classifier. Now, you must be wondering why it is called so. The naive Bayes algorithm is called naive because it makes the assumption that the occurrence of a certain feature is independent of the occurrence of other features. For instance, if you are trying to identify a fruit based on its color, shape, and taste, then an orange-colored, spherical, and tangy fruit would most likely be an orange. Even if these features depend on each other, or on the presence of the other features, all these properties individually contribute to the probability that this fruit is an orange, and that is why it is called naive. As for the Bayes part, it refers to the statistician and philosopher Thomas Bayes and the theorem named after him, Bayes' theorem, which is the base for the naive Bayes algorithm. As already mentioned, the basis of the naive Bayes algorithm is the Bayes theorem, which is alternatively known as Bayes' rule, or Bayes' law. It gives us a method to calculate the conditional probability, that is, the probability of an event based on previous knowledge available on the events. More formally, Bayes' theorem is stated as probability of the event B given A is equal to the probability of the event A given B multiplied by the probability of A upon probability of B. Let us understand the statement first, and then we will look at the proof of the statement. The components of the above statement are: P of A given B is the conditional probability of occurrence of event A given event B is true. P of A and P of B are the probabilities of the occurrence of event A and B respectively. P of B given A is the probability of the occurrence of event B given event A is true. Let us look at commonly used terminology in the Bayesian method of probability. A is called the proposition, and B is called the evidence. P of A is called the prior probability of proposition, and P of B is called the prior probability of evidence. P of A given B is called the posterior. P of B given A is the likelihood. This sums up the Bayes theorem as posterior is equal to the likelihood multiplied by posterior prior probability divided by the evidence prior probability. Let us take an example to better understand Bayes' theorem. Suppose we have to draw a single card from a standard deck of 52 cards. Now the probability that the card is a queen, which is P of queen, is equal to 4 by 52, which is equal to 1 by 13. If we are given evidence that the card that we picked is a face card, the posterior probability, P of queen, given face can be calculated using Bayes' theorem as P of face given queen multiplied by P of queen upon P of face. Now P of face given queen is equal to 1, because given the card is a queen, it is definitely a face card. Now we have already calculated P of queen, so the only value left to calculate is P of face, which is equal to 3 by 13, as there are 3 face cards for every suit in a deck. Therefore, P of queen given face is equal to 1 by 13 into 13 by 3, which is equal to 1 by 3. The derivation of Bayes' theorem is fairly simple and straightforward. The conditional probability, P of A given B is equal to P of A intersection B upon the probability of B. Here, P of A intersection B is the joint probability distribution of 2 events, A and B. Similarly, P of B given A is equal to the P of B intersection A upon the probability of A. Now, combining both the equations, we get P of B given A times P of A is equal to P of A given B times P of B. Shuffling the terms, we get P of A given B is equal to P of B given A times P of A divided by P of B, and hence Bayes' theorem. Now that we have understood Bayes' theorem thoroughly, let us look at the form that Bayes' theorem takes for the naive Bayes algorithm. In a machine learning classification problem, there are multiple features and classes, say C1, C2, up to CK. The main aim of the naive Bayes algorithm is to calculate the conditional probability of an object with the feature vector x1, x2, up to xn, which belongs to a particular class, Ci. That is, the probability of Ci given x1, x2, up to xn, which according to Bayes' theorem is equal to P of x1, x2, up to xn, given Ci, the probability of Ci upon P of x1, x2, up to xn. This is to be calculated for all the values of I ranging from 1 to k.